Hello, can you hear me? Anybody?
Yes, we can hear you.
Okay, so I have my talk is although the third talk, but I just wanted to make sure that my mic and connection is fine.
I'm sorry, can you speak up a little bit? You have your talk ready?
Like my talk is the third talk, but I just want to make sure that my mic and connection is fine. Can you hear me fine?
Yeah, absolutely.
Okay, thank you.
Looking forward to your presentation.
Thanks.
Mm-hmm.
Colleagues, good morning. If you want, you can try your presentation, try to demonstrate it.
Hi, Jean. Are you here? Can you?
Yeah, I'm here.
Okay, excellent.
Yes.
Can you try showing your presentation?
Yeah, could you see it?
Yeah, perfect.
Yeah, okay.
Excellent.
Thank you.
All right. Georgi?
Yes, Alexei.
Yes, hi. So maybe we should start.
Yes, I think we can start now.
All right, perfect. All right, so welcome to the last day of Lomonosov conference. Today we have a very exciting session on charm physics. My name is Alexei Petrov. I'll be chairing this session. And please make sure that you stay within your allotted time. So I'm going to give you a warning after 15 minutes of your presentation. And really, this is a time where you should start building towards your conclusions, because we will have a couple of questions probably at the end. So with all of that, again, welcome to this charm session. Our first speaker today is Haijing Li from Henan Normal University. And the talk is about recent results of charm physics at BEST3. Please go ahead. And by the way, please mute your mics for those who don't speak.
Could you hear me?
Yes.
Okay. Hello, everyone. My name is Huijing Li. Just on behalf of BEST3 collaboration, I will give a report about the recent results of charm physics at BEST3. Here is the outline. So I will just focus on the two parts. One is the pure and semi-leptonic decays, and then is the hierarchical decays. First, I will just introduce our main goal. For the pure leptonic and semi-leptonic decays, the measurements of the branching fraction is a bridge to measure the product of the deconstants and the schema matrix. So we can estimate the deconstants if we input the value of the schema matrix with CD or VCS, which will be very useful to calibrate the lattice QCD. On the other hand, if we input the value of the deconstants of on batch, we can measure we can estimate the schema matrix elements, which is helpful to test the integrity of the schema matrix. And we can also use our measurements to test the lepton flavor universality. For the main goal for our hierarchical decays is to measure the strong phase difference, since strong phase difference with the quantum correlated setup parameter DD0 bar, which is the important input for the determinations of the gamma angle, and also to study the charm missing and direct CD violations. Here's the next two slides just shows a brief introduction for our collider BPC2 and our detected BEST3 detector. This table just shows the data sets used in those analysis. In those analyses for D0, we use the psi double prime data sets. The integrated luminosity is about 2.9 inverse sigma. And for the D sub S case, we just use the six data points. The total integrated luminosity is about 6 inverse sigma. Okay. Let's introduce our analysis. We just based on the double tag analysis. The left is for the for a simple view of how to generate the DD pair at the center energy of center prime, and the right one is for the D sub S analysis. analysis, we just first fold for those for both D and DS analysis, we just first fully reconstruct 1D or DS using those variables, and then in the reconcile of the single tag D, we analyze the signal D plus just within those variables listed here. And finally, the signal branching fractions is calculated with this branching fractions, where the signal, where here the epsilon means the signal efficiencies. And in the analysis, the charge conjugated processes are also implied. Let's first introduce our pure leptonic decays. For the pure leptonic decays, just focus on the D sub S decays. And the first analysis is D sub S to tau nu, where tau is reconstructed with inunion. For this analysis, we use the variable the total energy of good photon, good EMC shower, just excluding those associated with the single tag candidates and those within 5 degrees of the initial direction of the positron. And the double tag yield in within 0.4 degree is obtained by subtracting the background yield, where the background yield of D sub S to the X nu, where X means the particle, that means the particles exclude the K long and as well under our signal. The background yield of DS to X nu is extrapolated from the fade to the high side, and finally we obtain the branching fractions of DS to tau nu, which is the most surprising result to date. And next is it's also DS to tau nu, but tau is reconstructed with pi plus pi by 0 neutrino. We just perform the simultaneous fade to the Misimas square for 6 energy points. Those phases are just shared with the common leptonic branching fractions. And the singular yield is about, and the singular yield is listed here. Finally, we just we also calculate the branching fractions. The third analysis is also DS to tau nu, but tau is reconstructed with pi nu. For this analysis, we just perform unbind simultaneous maximum likelihood to the 2-dimensional distributions of the invariant mass of the tag DS and the Missima square. And here just shows we just split the sample into two categories. One is for the mu-like means the signal is means DS to mu nu is dominant, and this is pi-like means our signal DS to tau nu to pi nu is dominant. Finally, we obtain the signal yield for DS to mu nu and DS to tau nu and DS to mu nu, as well as the branching fractions. For the branching fraction of DS to mu nu, this result is the most surprise to date. And then we just test the lepton flavor universality by combining the results from baseline measurements and the PDG value. The value here, this is the measured value, which one can see that it is consistent with the value from standard model prediction, and so there is no lepton flavor universal. There is no variation in tau nu flavors with the current precision. And then we just also showed, and then this plot just shows the comparison of the decay constants. The red one are from base-free measurements, and others is from clear other experiments. And here, this table shows the comparisons of the Secant matrix VCS. Next part is semi-leptonic DS decays, D or D sub S decays. First analysis is D2 eta mu, we just perform the ambient feed to the UMIs and obtain the signal and branching fractions. We also estimate the ratio of D plus 2 eta mu nu over D2 eta E nu, and finally the result is consistent with the standard model prediction. So there is also no leptin fluid, there is no variation in current within current sensitivity. And then we just performed the first measurements on the dynamic of the D plus 2 eta mu nu decays. The left plot is the partial decay rates over the 4 momentum transferred square, and the right one is the form factor. And here shows the measured result. Next is desired to K1 in U. K1 in U where K1 decays to K plus K pi. We just perform the 2-dimensional ambient extended maximum likelihood simultaneous phase shared with the same value of the leptonic decays. One dimension is the missing mass square, and the other is the invariant mass of K pi pi, where the peak is just the mass of is the K1 stage. And we also obtained the ratio of desired to K1 in U and D plus to K1, D plus to anti-K1 in U. The result just shows the agreements with the results just agrees with the unity as predicted by isospin symmetry. And then next analysis is the DS2S in U. Here the X means the inclusive decays. And we just sort the record side, selected the tracks into 18 momentum beams for the momentum greater than 200 as the signal yield calculated with this formula where the signal yield with momentum less than 200 is extrapolated from the high side. And we also measure the signal yield and branching fractions, as well as the ratio of DS to S in U over desired to S in U. But this result is consistent with the prediction. Okay, let's switch to Hierarchical decays. Hierarchical decays. The DD pair, the produced DD pair is quantum correlated decays. So we can directly measure the strong phase difference between the D0 and D0 bar decay. And here this plot just shows the Dali's approach for the D2 or K short pi plus pi minus, where the single tag mode is CP even or CP odd. And the strong phase difference result just shows the bottom plots, just based on 3 schemes: equal binning, optimal or modified optimal binning. And the estimate uncertainty on the gamma angle is between 0.7 degree and 1.2 degree. Next is for the D to K short K long KK. This analysis just based on the equal strong phase different spinning, but with 2, 3, 4 pairs of beams. Just shows the plot also shows the bottom line, and we also estimated the uncertainty on gamma angle. And then is D2 K3 pi and D2 K pi 0. We perform a chi-square fit to obtain the covariance factor and the strong phase difference. And besides the strong phase of D2 K3 pi is divided into 4 beams. Just based on this result, we also estimated the uncertainty on gamma angle is around 6 degrees. Next is D plus 2 K pi 0. This analysis is the double capillary suppressed decays. Since the naive expectation for the double capillary suppressed over the capillary field is the order of the first power of 19 theta. We just perform the 2D fit for all events and perform simultaneous 2D fit for the omega events in omega signal region and omega theta band region. Finally, we obtain their yield. And then we measured their branching fractions and fractions. The ratio of the double capillary suppressed of D2 K3 pi over D2 over the capillary field is also calculated, and we found that this ratio is significantly larger than the value from other double capillary suppressed. Okay, and then last is our summary. Just within the two kinds of data samples. One is for D and the other is for DS. Both has started the pure and semi-leptonic DS decays and the charm hadronic decays, where the strong phase measured from the charmonium hadronic decay is the key input for the determination of gamma angle. And in the future, basically we collected more data sets. The single precision will be further improved, and we hope a new era of precision charm physics. Yeah, that's all. Thank you.
Thank you very much for this very nice and informative talk. Are there any questions? I don't see any raised hands, but I have a short question. So on page 13, you talked about, yeah. So you have this ratio for lepton flavor universality studies. What are the perspectives of measuring similar ratio for radiative decays, where you have photon, in the decays in the numerator and the denominator?
The denominator we just is about 0.1, 1%. Yeah, well, I suppose we have just perform the correction.
Because it's yet another possibility for studies, those lepton flavor violating decays that are not restricted by two-body kinematics, which makes other new physics operators, if those are responsible for lepton flavor universality violations, to come in. So that's basically the idea. Would be nice if you can measure them in the future.
Okay.
Are there any other questions? Well, if not, let's thank the speaker again.
Okay, thank you.
Thank you very much. So our next speaker is Xiaoping Win from Fudan University.
Hello, can you hear me?
Oh, you're here. Excellent. So she'll talk about recent searches for exotic germanium-like states at BES3.
Can you
Please.
see my screen?
Yes.
Okay. Hello, everyone. My name is Xiaoping Qin on behalf of BES3 collaboration. Today I report the recent search for exotic germanium-like state at BES3. This is the outline. I only introduced the results for the XYZ in recent 2 years. The process list here. Many exotic germanium-like states, i.e. the XYZ, have been discovered in the quark-gluon spectrum. The XYZ shows properties inconsistent with expectation from established quark models. The BES3 detector and the BBC2 collider can be found in the previous BES3 report. The BES3 data for XYZ study can be seen in the plots. We use the data from 3.8 to 4.94 GeV with the integrated luminosity 22 fermitol inverse bar. The first is the X3872 studies. We study the process, the X3872 state in two process, E plus E minus decay to the pi. Sorry. The first is in the E decay to gamma X3872, X3872 decay to D star 0 and gamma D plus D minus. BES3 observed the X3872 decay to D star 0 D0 bar with statistical significance of 7.4 sigma. No evidence signal for the X3872 decay to gamma D plus D minus, gamma D0 D0 and pi 0 D0 D0 bar are found. In the same process, we search for the X3872 decay to the gamma JSI and gamma psi 2s. BES3 find evidence for the X3872 decay to gamma JSI with statistical significance of 3.5 sigma. No evidence signal for the X3872 decay to gamma psi 2s is found, but the ratio between the branching fractions of the X3872 decay to gamma psi 2s and the branching fractions X3872 decay to gamma JSI is 0.59. X3872 state is more likely a molecule or a mixture of molecule and germanium rather than a pure germanium state. For the second process, E plus E minus decay to pi 0 X3872 gamma, we also search the ZC4010T with zero charge decay to X3872 gamma. Since no significant signal are found, we provided the upper limit on the cross-sections cross-section E plus E minus decay to pi 0 X3872 gamma test the branching fractions of X3872 decay to pi JSI. The results are no conflicts with the theoretical expectation 0.1 fermitol bar. We define the signal range of the X3872. Then we also measure the cross-section E decay to the pi 0 ZC4010T test the branching fractions of ZC4010T 0 decay to X3872 gamma and X3872 to pi JSI. We measure the ratio of the branching fraction ZC decay to X3872 gamma over the branching fraction ZC decay to the D star with zero charge. The ratio is less than 0.15%. The ratio doesn't construct the prediction based on the molecule picture. For the study of the Y state, we study the E plus E minus decay to the pi 0 Jsi from 3.8 to 4.6 GeV. In the cross-section distribution of the EE decay to pi 0 Jsi, we can see two resonances in the cross-section. They are the Y4210T and Y4310T. The mass and width of the Y4210T are measured to be 4210T.4 and 46.2. The results agree with those previous results pi Jsi and confirm the existence of the harmonic less than Y4210T. The significance of the Y4310T is estimated to be 4.2 sigma. The ratio of the cross-section pi 0 Jsi and the cross-section pi Jsi is 0.48. The ratio is consistent with the prediction 0.5 based on the isospin symmetry. In the same process, we search for the ZC 3900 with zero charge and the pi 0 Jsi mass spectrum. Use the simultaneous partial wave analysis to perform on the four data sample. The structural ZC 3900 is clearly observed. The mass and the width are measured here. The JP is 1 plus. We also measure the cross-section of E decay to pi 0 ZC decay to pi 0 Jsi. The structural Y4210T is observed in this process. The mass and width of the Y4210T are measured to be 42, 31.4 and 41.2 math. The relation between the two exotic Y4210T and the ZC 3900 with zero charge is established for the first time. We also measure the E plus E minus decay to eta Jsi, and three structure can be found in the cross-section light shape. Assuming the lowest lying one is the psi 4040. The Y4210T and 4390 are observed in the process. Y4390 are observed in the process with statistical significance of 6 sigma for the first time. The mass and width of the Y4210T and 4390 are consistent with or close to the previous result. The nature of the difference on width is still unknown. We also measure the EE decay to eta psi 2s. The signal yield are determined by the Feynman-Cassis method. The process is observed for the first time with a total sample. The significance is 4.9 sigma. And we provided the upper limit on the cross-section, and we found, and we can see a enhancement around the 4.26 GeV. In the future, a partial event reconstruction technique might improve the detection of this process. We measure the cross-section E plus E minus decay to the pi psi 2s. In the cross-section light shape, we can see three structure: Y4210T, Y4390, and Y4660. The corresponding significance of the three structures are 4 sigma, 16 sigma and 8.1 sigma respectively. For different process investigated in ABS3 experiment, Y4390 states are consistent among different decay modes with uncertainties. The rise of the Y4220 is smaller than the previous result. For the Y4360, Y4390, and Y4660 observed in the PyPy per as processed by BES3 Bell and Baba experiments. The mass of the Y4390 observed by BES3 are larger than that of the Y4360 observed by the Bell and Baba, but these results can still be considered as consistent results. The measurement of the E plus E minus decay to the gamma Cascade J cross-section. We use the data from 3.773 to 4.6 GV. E decay to gamma Cascade 1 and E decay to gamma Cascade 2 are observed for the first time with the significance of 7.6 sigma and 6 sigma. We provided the cross-section light rate of the E decay to gamma Cascade 1 and Cascade 2, and the upper limit on cross-section of the E decay to gamma Cascade 0. For the cross-section light of the E plus E minus gamma Cascade 1, it can be described with the conventional Charmonian resonance, and one resonance with significance of the 5.8 sigma is observed in the light shape of the cross-section E plus E minus decay to gamma Cascade 2. The mass and the width are measured to be 4371.7 and 51.1 MeV. The results support the Y4360 or Y4390 decay to gamma Cascade 2. The measurement of the E decay to gamma Cascade J cross-section are consistent with the potential model predictions, except for the branch fractions of the PSI 4160 decay to gamma Cascade 2. The branch fractions is larger than the theoretical predictions. Let's go to the study for the least days. The Charmonian light structure have been observed in the pi and Charmonian mass spectra, and can be found in these experiments. The first one is the E decay to Cascade J pi and search for a Charmonian light structure decaying to Cascade J pi. Use the data from 4.18 to 4.6 GV. No significant signal have been observed. So therefore, we provide the upper limit on the cross-section of the E decay to Cascade J pi. No Charmonian light in the mass spectra of the Cascade J pi subsystem. Hence of a slight enhancement for the E decay to Cascade 1 pi around the 4.23 GV here. We measure the E decay to eta C 3 pi, eta C 2 pi, and eta C pi 0 gamma. Then search for the ZC decay to eta C pi. Use the data from 4.18 to 4.6 GV, eta C decay to 16 decay mode. Use the simultaneous feed for all eta C decay channels to determine the signal yield. The process E decay to eta C 3 pi is observed for the first time, and we can see the Y4260 resonance can decay to the eta C pi plus pi minus pi 0 final state. We also provided the upper limit on the E plus E minus decay to the eta C pi and eta C pi 0 gamma in these two plots. Then we search for the eta c decay to eta c pi, and the process E plus E minus decay to the eta c 3 pi. The search is realized in terms of a mass and width scan for the ZC. Use the simultaneous feed for all eta c pi decay channel. ZC 0 decay to eta c pi 0, and these processes are found to be more significant. We also search for the reaction channel E plus E minus decay to eta c eta pi pi. Eta c also decay to 16 decay channels. The cross-section, the upper limit on the cross-section are provided here. Since no signal is observed, and it is impossible to conclude about the possible resonance structure in the final state subsystems. The last one is the ZCS study. We study the E plus E minus decay to K plus DS minus D star 0 and K plus DS star D 0 at 5 energy data. We only reconstruct the K plus and DS, while DS decay to KK pi and K short decay to pi pi. Fit to the K plus required mass spectrum for 5 data sample. And an enhancement with 5.3 sigma is observed near the mass threshold of the DS D star and DS star D bar. The mass and width are 39, 85.2, and 13.8 MeV. We name the enhancement as ZCS. It is the first candidate of the hidden charm tetra quark with heterogeneous. The bond cross-section E plus E minus decay to K plus ZCS tests the bunch fractions for ZCS decay to DS minus D star 0 and DS star D 0 decays are measured at 5 energy point. And we can see an enhancement around the 4.68 GeV. We need a further study to confirm the Y4660. Let's go to the summary. The best three, the XYZ data, the XYZ state are studied at best 3. We report these results at this process. More results for XYZ state at best 3 will come soon. Thank you for your attention.
Well, thank you very much for your talk. Very nice. Are there any questions? Okay, I don't see any raised hands. I actually have a sort of a silly question. Have you tried searching for decays of X3872 to light quark states without the germanium or Ds in the final state?
Can you repeat again? I don't hear
Right.
clearly.
Have you tried searching for decays of X3872 to the light quark states? That is to say, to the states that don't have J psi or eta sub c or DD bar in a final state, like an case. Like X3872 to like 3 pions, for instance, or something.
32.
No, if not, that's okay. It's just, you know, maybe something for the future.
Sorry, I can't. Sorry.
That's all right. All right. Any other questions? Well, if not, let's thank the speaker again. So our next speaker, yes, thank you. Our next speaker is Yasha Vahid from KK.
Okay, let me share my screen.
Mm-hmm.
Okay, you can see my screen now.
Perfect. She'll be talking about latest results on beauty and charm hadron decay at Bell 2. Sorry. Go ahead.
Okay, so my name is Aisha. So as they said, I'm going to talk about some results from charm and on behalf of Bell 2 collaboration. That is the outline of my talk. So I'll introduce my experiment and then not all, but some important and recent decay measurements that we have performed, and then the outlook. So the rich phenomenology of the weak decays has always been a source of information about the nature of the elementary particle interaction. So these weak decays of beam meson containing heavy quarks are implied for the test of standard model and the measurement of its parameter. Particularly, they offer a very direct way to determine the weak mixing angles, test the unitarity of the CKM matrix, CPU violation, and hopefully this will provide us the hints for the new physics beyond the standard model. So these electron-positron experiments at epsilon 4s resonance provide a lot of information on heavy quark decays, like these P factors like SLAC and KK. They have certain advantages compared to a hadron collider. For example, they have very clean environment, which enables us to enable us to detect the neutral particles very efficiently. Also, these BB bar pair produced provide effective flavor tagging efficiency. So like you can see that for Bell 2, it's about 34% compared to what we have around 5% for LHCb. We have large tau samples. Also, the full reconstruction tagging is possible so that it becomes a very powerful tool to measure the B2U semi-electronic decays for the CKM matrix element measurements, and also for the decays which have large missing energy. So SuperKEGB, so it is an electron-positron, asymmetric electron-positron collider with the center of mass energy at BB bar threshold and 0.58 GeV. As we talked about before, that electron-positron colliders are clean compared to a PP bar collision. So we aim to SuperKEGB. This is the schematic for the collider, and which is a successor of KEGB, aims at an integrated luminosity of around 50 inverse 8 bar, which is about 50 times more than what we had for Bell. But here the major challenge is to deal with the harsh beam background conditions. We plan to deliver collisions at a peak instantaneous luminosity of 6.5 × 10⁻⁵, which is like 30 times more luminosity of what we have for KEGB, which will be achieved by increasing the beam current to 1.5 times the beam current and decreasing the beam size 20 times more. So here, that's like you can see our data taking. So we had taken around 240 inverse femtobarns of data until this summer shutdown, and we were able to record the highest luminosity so far, about 3.1 × 10⁻34. So this is the schematic of Bell 2 detector. Again, this is designed to operate with a performance better than Bell 2, despite that having the large beam background conditions. So Bell 2 enables us to have K-pi separation compatible with Bell, because we already have a very good separation of kaon and pions at Bell. High reconstruction efficiency with very low trigger bias, a better reconstruction of the final state particles containing photons like pi0 or rho charged rho. Also, the neutral K-long mesons are efficiently reconstructed. We have better K-short efficiency. Since the detection of the decay products of 1B is very good, so it allows us to measure the flavor of the other B to be tagged. We can do it very precisely. Also, very good vertex resolution enables us to have to perform the measurements, including the missing mass, since the initial state is perfectly known. Also, the production of the large samples of charm and tau electrons enable us to do a lot of measurements. Oops, no, sorry. So that's like a lot of you can say like what we are doing at Bell2. There are a whole lot of measurements that we are performing and can perform at Bell2. Like there are 2 more talks from Bell2, the results from the charmonium and botonium, and also the results for dark sector will be presented. I will try to cover like some other important, not all, but some other important topics in my talk. So moving on, first is the charm lifetime. So at Bell2, these star mesons, which are coming from the electron-positron to CC bar decay, events are produced that boost, that displaces these charged or neutral D meson points from the point of production, approximately about 200 micrometer to about 500 micrometer. And the decay time is measured from the displacement vector projected onto the direction of the momentum vector. So where this like this is the mass of the D meson, the D charge or neutral D, and whichever we are measuring. So this charm lifetime requires the most important is the excellent vortex detector alignment, also the precise calibration of the final state particle momentum, and also the powerful background discrimination. So the data that we have already with Bell2 is already very competitive, but again, the main challenge is to control the systematics. We use 2 decays for D0. We use K minus pi plus, and for and also we use K minus pi plus from the D star tagged decay, and this is a very high priority samples. And we are selected to limit the backgrounds which are related to the systematics. So in these plots, like these vertical lines and the dotted lines indicate the signal region and the sideband region that we choose for the fit strategy for the lifetime measurement. So we performed an unbinned maximum likelihood fit to the time and the decay time uncertainty, as we said that we measured from here. So we choose through 2 regions from the previous fit for K pi and K pi modes. These are the plots for K pi and K pi decay modes. So this decay time uncertainty is calculated by propagating the uncertainty in the 2 vectors of the length and the momentum. Like we have. So these model, the PDF has been modeled by the 2 Gaussian for D0 and 1 Gaussian for charge D, and their resolution is allowed to fit in the allowed to float in the fit. In terms of background, D0 background is very small, so we neglect that background, but we include the corresponding systematic uncertainty for that, and for D plus, we include the background in the fit and which is modeled using the data sidebands done in the previous fit. Again, the main source of systematic is coming from the misalignment of the vertex detector and also for the background modeling of charge D. So these are the preliminary results. So this is the most precise measurement till date, and it is also consistent with the previous measurement or the PDG 2020 measurement. So few per milli accuracy already established that the excellent vertex capability of Bell2. These are the results for the lifetime measurement of D0 and D plus. We also measured the ratio of these lifetimes, assuming that all systematic errors are correlated between D0 and D plus. Oh, sorry, that's a typo. That should be D plus. And the correlation is about 18%. Moving on to B to K LL measurement. So it's an important flavor changing neutral current decay measurement where like this L is either electron or muon. This is sensitive to many standard model extensions because this is suppressed at the tree level. So this is the measurement for a rediscovery of B to K LL. We use BDT to remove The inclusive B decays, where the variables that we use for in our boosted region trees are related to the event shape, and the variable related to the vertex, and the missing energy variables. So that will help us suppress the background coming from the light quarks and the inclusive B decays. So this is the first observation which we performed with the 63 inverse Femtobanov data by performing a two-dimensional fit to the delta E and MBC distribution, and that's the signal yield that we were able to calculate, which was about 2.7 sigma with 2.7 sigma significance. But of course, we need more data to have full branching fraction measurement and RK measurement. Moving on to B2K nu. Again, it's also a very important measurement for the complementary probe of beyond standard model scenarios, which were proposed to explain the many flavor anomalies. The standard model, beyond standard models like leptoquark, Exion, or the dark matter, these can be constrained from this measurement. This is the standard model prediction for this B2K nu decay. Experimentally, it's very challenging. Since we have two neutrinos, so we need information from the other B. That's why we use inclusive tagging approach, where we exploit the distinct topology and the kinematics to achieve higher signal efficiency, about 4%, which is better compared to the approaches that we have used before, like the semi-electronic tagging or the hadronic tagging. In this, we use two boosted decision trees in these classifiers. So one is the nested one, which the aim of that. The second one is to find the base background that are coming from the inclusive decays. So we select the highest PT track as our K1 candidate. The continuum background is modeled by the off resonance data directly, and then we validate BDT using data from B2J psi K, where J psi goes to play mu plus mu minus. So where these muons can be removed to mimic signals. So you can see this plot where we have the signal-like sample where the muons are removed, and this is used for the correction of this K1 candidate momentum. And this is the background-like samples where the muons are not removed. So we compare our BDT in data in Monte Carlo, and then, as I said, we correct K1 momentum using the simulated signal events. The fraction of the events in the signal region, so this BDT region is over that our simulation is 1.06 with an uncertainty of 0.1, which is quite good. So that's the preliminary results. So no signal observed yet, but we were able to set up upper limit on the branching fraction, but assuming with a standard model signal. And that's the upper limit for the branching fraction. If we able to convert the same luminosity or the same signal sample that we have for the previous measurement, this measurement is better compared to the measurement performed with the semi-electronic tag in about 10 to 20%, and with the hadronic tag by a factor of 3.5. So for future, of course, we need more data. We are planning to have add additional channels like K star 0 nu or K short 0 nu decays, and also improved techniques for the neural network, and hopefully we will be able to observe it with about 5 inverse Femtobanov data. So yeah, so we are working in progress for the improvement of the measurement of the inclusive tagging method, which we have already seen that it's better than the semi-electronic or the hadronic tagging method. Okay, moving on to B2 charm decays for the measurement of phi3. So these decays, B2 decay, these are important for the precise measurement of angle gamma or phi3. For Bell and Bell 2, like B2D 0K short pi pi, this is called as like a golden mode for the measurement of phi3 in both Bell and Bell 2. Here the dominant clean channels like the neutral D star pi and the charge D star pi provide a good control sample for these measurements. So what we do is that we perform a signal enhanced. We have a signal enhanced sample, that MBC greater than 5.27, and we have pion and cation enhanced sample. We're applying the particle identification on our signal B, and then we perform an ambient maximum likelihood to the delta E distribution and the output of the neural network, which was trained by using event shape variables. So we have with the 63 inverse 1:1 of data, we performed the fit, and we were able to get the ratio of B to DK over D pi, which is consistent with what we have with the PDG, which is obviously dominated by the LHCb measurement. And but yeah, we have advantage of calculating this ratio is that like many systematics cancel out. So we have a very precise measurement for the decays, which are systematically limited. But of course, the main aim is to have first Bell and Bell 2 measurement 453, which is for which the results are coming very, very soon. Okay, moving on to semi-electronic. So first of all, B2C and B2C and B2U LU decays. So different analysis strategies will help resolve this inclusive and exclusive discrepancies in the measurement of B2C LU and B2U LU, like basically VCB and VUB. So we measure Q-square moments in order to simultaneously determine the non-perturbative elements and VCB. Bell 2 have performed both untagged and hadronic tagged analysis for the measurement. I will be talking about just untagged analysis of an untagged analysis where we required one well-identified lepton, and we explored missing mass and momentum to reject the backgrounds, and then we were able to measure the branching fraction by performing the fit to the lepton momentum. Moving on to exclusive B2D LU decays. So exclusive decays have been explored again with both tagged and untagged approaches. In the tagged analysis, the background is very, very small, although we have less efficiency, but the background is very small. So what we do is that we calculate our signal from D star and D0 invariant mass and the lepton from here. So that's like the distribution of the missing mass square. And we are able to calculate the branching fraction of neutral B to D star L nu. We also perform an untagged analysis. Here, our variable is the angle, that theta by, excuse me, theta by, which is the angle between the B vector and the D star L vector. So that's the variable that we used for to perform the fit, and we calculate the measurement of the branching fraction with the 63 inverse 10⁻⁴ of data for charge B to D0 L nu L decay. But of course, many other decays and measurements are being performed, and then like the eventual goal is to measure the VCB from both inclusive and exclusive decays. So in the end, Bell 2 is in great shape already. We have about 200 greater than 200 inverse 10⁻⁴ of data, but yes, more results are coming soon. There are already more results, but I just happen to include a few very recent ones. By the measurement of the world's best D lifetime measurement, we already established the excellent vertex performance. First measurement of B2 nu U, B2 K nu nu, with the prospect of measuring the full branching fraction measurement of this decay. Also, re-optimization of Bell for phi 3 measurement. So that will be a first combined Bell and Bell 2 result. So within next few years, Bell 2 will be able to address the inclusive and exclusive VCB tension by precisely measuring the semi-leptonic decays. SuperGEC-B has already set a new world record in the peak instantaneous luminosity, and we are entering in the regime of to be called as a super B factory. And Bell 2 is also working very well and producing promising results. So yeah, looking forward to an exciting era in the coming decade where we have exciting discoveries and a healthy competition and complementarity between Bell 2 and LHCb. That's right. Thank you.
Thank you very much for this very informative talk. Are there any questions?
Okay.
If I may ask a question. So you talked about your excellent vertex performance, which gave you this fantastic measurement of the lifetime. Is it possible to do, I mean, do you have this best lifetime and the baryon lifetime measurements? In particular, what I'm curious about is this the lifetime of omega C baryon, which was actually found out by LHCb to be 4 times shorter than world average. Can you verify the result?
Okay.
Is there anything you can say about that?
Okay, so I'm like I'm like, this was from the PDG 2020, so I'm not sure if that measurement includes in that. But again, this is not my analysis, so I'm not sure. I'm not the perfect person to answer that question. Yeah, so I like for in terms of like these measurement that was I think compared here, but I am not sure for the baryon that you're mentioning.
Okay, that's fine. That's fine. All right, thank you. Are there any other questions? If not, let's thank the speaker again.
Thank you.
And thank you. So the next talk is by Pavel Kirkovni from Butker Institute of Nuclear Physics. Pavel?
Okay, I'm here and I'm trying to share my screen. Okay, this talk.
So he will be talking about the BEL2 prospects for germanium and batamonium studies. Still the same.
Can you see my slides?
Yeah, but there are black boxes. Is
Yeah,
it supposed to be?
It's from due to Zoom, and I can't avoid it because I can't share the application. I can share only the entire screen.
All right. Well, let's see if it works. Go ahead.
Let me try to move it somewhere. Okay. I'll present BEL2 prospects and results on germanium and batamonium studies. Okay, so probably you already know that Super KKB Collider is an upgrade of
Oh, sorry, you still have a black box in the top right corner, which pretty much covers like 1/6 of your slide. Can you do Control L and view the whole document? Or remove that black box.
I don't have any black box on my screen.
What we can see, yeah, there is a black box, which is like a bigger one.
Can you try to show the presentation in a full screen mode?
It's already in full screen mode.
All right. Then you can try to move the whole presentation to the left. All right. Now you're moving the black box. You've just moved the black box. It's yes. Okay. Now it's fine. You can turn to the full screen.
Okay. Thanks. Okay. So the major improvement in the luminosity should come to the fact that the focus in the interaction point is much stronger, and beta function is reduced more than in order of magnitude, and this should result in more than order of magnitude improvement in the peak luminosity. So the goal for detector is collect 50 inverse afterburn. Just to comparison, the current statistics from Bell and Babar is less than 2 inverse afterburn. Bell2 detector, it looks very close to the Bell detector, but it's entirely new detector, new vertex detector, new drift chamber, completely new identification system based on the focusing aerogel and time of propagation counters. For the colorimeter, the previous crystals are used. However, entirely new electronics allowing waveform sampling and thus reducing the influence on the beam background due to pileup. And for the K-long and muon detection system, it's RPC for barrel outer layers, Simon Bale, and scintillator for the end caps and inner layers of the barrel. On this slide, you can see the best 1-day picture for the KKB collider luminosity. Actually, it is June 22nd. The peak luminosity exceed 3.1 times 10 to the 34, and integrated luminosity per day is almost 2 inverse afterburn. On the left plot, you can see the collected integrated luminosity, and currently it's exceed 200 inverse femtobarn. Sorry, here I mean that day luminosity exceed almost 2 inverse femtobarn, not afterburn. The data taking efficiency is about 90%, but results, what I'm going to show, is based on the part of the luminosity, about 60 to 70 inverse femtobarns. On this slide, you can see the picture with Charmonia states, starting from the bottom eta C, J psi, and so on. And you can see by black conventional Charmonia, shown by blue is unconventional neutral states, by pink unconventional charged states, and by red pentacore candidates. And well, below kinematic threshold, it's mostly bound states, and above thresholds, a lot of wide complex states. At B factory, we can produce Charmonia by 4 ways. First, by B decays, for example, B2K and CC bar, which allow us to produce different JPC combination. Another way is ESR, where electron-oppositron have radiated the gammas, thus reducing the total central mass energy, and then CC bar is produced from virtual photon here, and only 1 minus can be produced this way. Third is 2 photons process, where both electron and positron produce 2 gammas, and they produce CC bar. Again, some different quantum numbers of states can be produced, and another way is double Charmonium production in plus and minus annihilation. The most known and interesting and puzzled particle and charm sector is X3872, or as it mentioned and recently in PDG, high sub-C 3872. It was observed by Bell almost 20 years ago, and then detailed studied by both B factories and LHCb. So currently we have we know its mass, have some information about widths, but still many puzzles. For example, the line shape, you can see on this plot from LHCb that if we have, for example, if we describe its shape by Flatter, but then or by Breit-Wigner, and after we apply the Smerian due to detector resolution, we see actually no difference for the experimental data. That's why it's very hard to find the actual from the experimental data, find the actual shape of this state. Decay ratio is also not very well known. About one third of the decays are unknown. And the real nature is also a big question, because it's just on the threshold of DD star, and actually we don't know if it's above threshold or below threshold. So any new information on this state is necessary. On B factory, we can produce it from B decay to X3872 and Cairn, and then it decay to J-psi and to pions, mostly dominated by ρ0 meson, and then J-psi is reconstructed in A plus minus or plus minus. So current build 2 sample is 63 inverse femtobarn, and we reconstruct this decay channel using basic selection, continuum suppression, particle identification, and kinematic variables, pi invariant mass, beam constraint mass, and delta E or energy difference. As a control channel, B to psi to SK was used with exactly the same final state. And you can see the experimental data on the top plot, where J-psi pi invariant mass is shown. You can clearly see psi to S signal here. And left is for K plus, B plus to psi to SK plus, and right is for B0 to psi to SK short. On the bottom, the same plots for the X3872, and about 15 events plus minus 5 was observed with more than 4 sigma statistical significance, and it's expected what we should have comparison with previous Bell data. Another way to study germanium is ESR production, and here you can see results for the E plus and minus to pi J-psi by ESR. Again, selection is based on particle identification, J-psi invariant mass reconstruction, and recoil mass to pi J-psi signal. And on the plot, you can clearly see psi to S signal reconstructed in M plus M minus, and where J-psi is reconstructed in M plus M minus and M plus M minus. Next step is Y4260 rediscovery, and we expect about 60 events at 100 inverse femtobarn. For the bottom ammonia, we can produce it directly from the A plus and minus by ESR. Both only one minus states can be produced, upsilon NS. Also, hadronic transition from upsilon through eta or pi, where we can produce another upsilon, H sub B, eta B, and so on. Also, radiative transition from upsilon, where high sub B can be produced, and also electric dipole transition, where we can produce eta B, and also magnetic dipole transitions. On this slide, you can see the cross-section of plus and minus to BB bar, where you can see the upsilon 4s, the main energy for the B factory, but also we can scan to the low and to the high energy to look for upsilon 5s or even upsilon 6s. The first result for build 2 is study of dipole transition from upsilon 4s. You can see on the right two-dimensional plot where M plus M minus invariant mass is shown on the Y, and invariant mass difference pi m plus m minus minus m plus m minus invariant mass is shown on the X. And you can see on this plot some areas where we have 4s, epsilon 4s to epsilon 2s pi transition, also some transition from epsilon 3s and even epsilon 2s. And this is 70 inverse Winterborn early build-to data, and we verify that we see what we expect. And next is study of invariant mass of pi from epsilon 4s transitions. For the build-to potential is to run at higher epsilons and do an energy scan in order to search for predicted or new resonances such as missing bottom-only exotic states, improve precision of already known process, and for example, ZBs, measure the effect of couplet channel contribution, study BB star and BS star threshold region. The later one can be challenging for super KKB, maybe available only after the upgrade. Also run at lower epsilon energies to search for missing pi eta transition and search for new physics here, such as lepton flavor, universality violation, new scalars, and so on. For the future plans, build-to and super KKB is going mainly collect data on epsilon 4s resonance. But this fall, we're also planning to collect some integrated luminosity at YB 1075.3 and also around it to have some additional points for BB body composition. So expected data is 400 inverse Winterborn by end of this year, and around 750 inverse Winterborn by summer of next year. After that is nine months upgrade is planned, then data taken till next 4 years, and we're expecting to have about 10 inverse Afterburn at the end of 2026. After upgrade, it can be possible to run at to take data at 11 GeV to study epsilon 6s production. And some further proposal is options for larger statistics on epsilon 6, 3, and 5s datasets. As a summary, I can conclude that build-to is next generation B factory, and Charmony and Bottomony are significant components of the physics program. Advantages with unique production decay modes related to the neutrals in comparison with Hadron Collider. We're planning to take data not only on epsilon 4s energy, and currently status is analyzing of early data, rediscovery of 1 BB bar states. Statistics should soon be comparable with Pabar and Bell, and also we are welcome for the inputs from the theoretical community on 10.75 GeV and other BB bar studies. Thank you. That's all.
Thank you, Pavel. Very nice talk. Are there any questions? So I don't see any hands raised, but I want to ask you the same question I asked a best 3 speaker. So have you guys looked at non-charmed, light quark decay modes of X3873? Something like rho pi plus pi minus. You see, there are different components of the wave function. You know, it's a molecular part, and there is a more compact tetraquark component. And depending on which component is represented in a larger state, the annihilation decays, such as decays to light quark states, would be larger or smaller. So it might be interesting to see if you could.
Yes, I got your point. It can be done, but we need to wait until we have statistics compared with the previous Bell one. So probably, actually on Bell it was already studied the hadronic decays of B mesons, and on these hadronic decay studies like B2K and 3 or 4 hadrons. As far as I know, it was not observed any hint for X3872.
Okay.
But the upper limit was not set. So
okay.
Probably it's a good idea to make some dedicated study and set the upper limit on the branching fraction. Thanks for this suggestion.
Mm-hmm. Are there any other questions? Well, if not, let's thank Pavel again. Our next speaker is Surapat Ekin from PFL Lausanne. Are you here?
Yes.
Oh, excellent. So you can share your slides. So he will talk about charm physics at LHCb. Please go ahead.
Can you see my screen?
Yes.
Okay, nice. So it's like, okay, hi, everyone. So my name is Surapat Ekin from EPFL, from EPFL Lausanne on behalf of the LHCb collaboration. Today I'm going to talk about the charm physics at the LHCb. So let's get started. So for the charm physics program at the LHCb, we have like 3 subgroups. So, but like for the today talk, I'm gonna talk about like only the mixing and CP violation, and also I'm gonna talk a bit about the production and the spectroscopy. And so for this talk, I will focus on the mixing and the CP violation, which I will talk about the first observation of the difference between the zero mass the organ state. And after that, I will talk about the time dependent CPV search, and also time integrated CPV search in the different channel. And then for the production and spectroscopy, I will talk about the lifetime of the omega C. So the next one is like for the LHCb experiment. So it is the forward spectrometer that is optimized to study the decay of the charm quark or the beauty quark. So this detector has a nice efficiency of the part of the PID, and also like a nice tracking efficiency. And it has been running since 2010, and it's like we are now in the long shutdown 2, and then it's like up from the run 1 and run 2, the data taking, we have collected up to around 9 inverse femtobarn. So there are like quite a lot of the data to analyze. So, and then it's like why the study of the charm production at the LHCb is quite interesting. So the first one is that because it's unique. So it's like because only uptype quark decay in which the new physics coupling can be probed here, and then we can do it as the discovery tool, such that the indirect CPV in the charm could probe the extremely high BSM scales, which are highly suppressed in the standard model. And also it's like we also have the larger cross-section of the charm decay at the LHCb. It means that we have the billions of the decay ready to be studied at the LHCb. And then it's like mainly at the LHCb, we can extract the charm sample from the 2 tag. The first one is the prompt tag, which we can use the chart of the pion to determine the flavor of the D0, or we can use the decay of the B meson and then use the muon here. Use the charge of the muon here to determine the flavor of the D0. Yep. And then for the mixing and CPV, so as you all know, so mixing, flavor mixing is the transition between neutral flavor meson and its antiparticle, and then this can be described by this equation, this Hamiltonian. So and then it's like from this equation, we can extract also the organ state with the organ value which I have shown here, and this organ value we can define the mixing parameter which are x and y. The x parameter is related to the mass difference between this mass organ state, and y is the difference of the decay of the lifetime between this mass organ state. So before like 2 months, before like 2 months ago, so like the mixing parameter in sham, it had not been measured with the high precision, because like to prove that if the mixing can occur in this sham system, like this row that can mix to the zero bar, so we have to measure that the x and y parameter is are non-zero. And then the measurement of this parameter are quite sensitive to probe the physics beyond the standard model. So in the standard model prediction, it has it predicted this x and y parameter to be in this range, which is quite a large range. For the y parameter, it has been measured to be like a non-zero for quite some time, but not the x1 in the 2019 here. So there are different type of the CPV scenario, as I show from this on this slide. So the first one is the direct CPV, which we can find the difference in the amplitude of the decay in the same channel, or in the we can also have the CPV in the mixing, like D0. The D0 has the mixing rate which is different from the 0 bar, for example, or the CPV in the case that there is the interference between decay and the mixing one. And then 2 months ago, we announced that there was first observation of the non-zero measurement of the x. So this one we did the analysis on the D0 to K short pi, and then we probe this this x parameter to be non-zero. And so why and how did we do that, and why this decay channel is quite interesting. The first reason is that this decay is the self-conjugate decay. It means that the reconstruction efficiency is equivalent between D0 flavors, and the D0 can decay to to K short pi in the different paths, as I show here. So it can go to the Kabibol flavor, doubly Kabibol subplace, or D0 can mix to D0 bar and then decay to K short pi while Kabibol flavor. And then this has a different region in the dialysis plot on this graph. This decay is also sensitive to the measurement of the x and y parameter, and also we can also measure the CPV. We can conduct also the CPV measurement of the Q over P, and also in the interference term. For the analysis approach that we did on this decay channel, so we can use the model independent method, which is known as the bin flip method. So this method, it measures the time-dependent ratio between positive and negative dialysis bin of the constant strong phase difference. So in this way, it gives the access to the mixing parameter, and then we can actually measure that. And since we did the so from this method, since we do the measurement on the ratio, so it means that it can suppress the biases due to the non-uniform event reconstruction efficiency, because like this efficiency is cancelled in the ratio. And then we did the analysis on the run-to dataset of the pion tag sample. So just to tell you a bit more about this bin flip method. So it's measure the ratio between the signal yield between the event yield in the wrong side here, which is the negative Dalis bin, and the positive Dalis bin here, which represent the right side, as a function of the decay time. And then we can expand the ratio in the different bin to be this equation, and then for the mixing parameter is embedded as the set here. And then it's like we also use the external input from the Clio and from the combination measurement of the Clio and the base tree. Like we use the strong phase difference, which is the XB over here. And the advantage of this method is that like at the limit of the CP conservation, so this method is like is sensitive to both X and Y parameter, but it's more sensitive to X parameter because of this term. And then in the run-to analysis, we have extracted around more than 30 million event of the prompt tag sample of the D0. And then we split the sample into the bin of the Dalis bin, and we also split the sample depending on the bins of the decay time. That we have the X bin of the Dalis bin here as the function of the decay time, and then we use that to fit with the bin flip equation that I show you in the last slide. And then we can measure the XCP and YCP to be this number. As you can see here, the XCP here is quite different from 0, and then we can also use the same method to measure the delta X and Y, which are related to the CPV parameters. That is like we can do the difference between the between this ratio between the D0 flavors, and from these four parameters, if we can parameterize that to X and Y, which are mixing parameter. And from the left plot here, you can see that with this measurement, so we can provide the first observation of a difference between D0 mass eigenstate with more than 7 sigma significance. But it's like if you look at the right plot here, the QOP parameter and the interference parameter are still consistent with 0. It means that there's no like a significant CPV is observed in this case. So, but we also have the upcoming result in the pipeline that we can actually in this decay channel, we can do that on also on the semi-leptonic tag, that we can also use the bin flip method to measure this mixing parameter and also measure the CPV parameter. The advantage of this sample is that it covers the wider decay time distribution, because like we select we trigger the event with the muon track, and then it's like we can use this bin flip method, and then we can combine the result with the prompt sample, which I have shown you before, or the as the alternative. So we can do the model dependent the amplitude model, in which we perform amplitude fit with the parameterized Dalis and decay time efficiency that we can model on the Monte Carlo sample. So the next one is that we can also do the search for the CPV in the time dependent CPV in the D0 to pi and D0 to KK. So in this case, we can define the asymmetry as the asymmetry in the production rate of the between the D0 and D0 bar. So we can define the asymmetry with this equation, and then this term can be expanded to 2 terms. The first term is related to the final state dependent CPV, which is suppressed, and the second term is related to delta Y here, which is usually known as the A gamma. And this one can be expanded to the mixing parameter. following this equation. And for the analysis procedure, we extract the raw asymmetry, and this one can be factored to this term, and then we can estimate the asymmetry from the detector of the pion tag, and then we can also estimate the production asymmetry of the D star. So, and then we did this analysis on the run-to dataset of the pion tag sample that we have extracted almost 60 million of the D0 to KK and almost 20 million events of the D0 to pi. We also validate the analysis procedure on the large sample of the D0 to Kpi, which we have around 520 million. That in this sample we don't expect delta y parameter here to be non-zero, which is the case. And then we use the same analysis procedure to measure the delta y on the D0 to KK and also D0 to pi, and we arrive at this number on the screen here. So these two numbers are quite consistent, and then it's we just combine this one, and then we also provide with the world-based average of this measurement of the delta y, or we may know as the A gamma. And so unfortunately, it's this number is still consistent with 0, which we haven't found the CPV. We haven't seen the CPV in this decay channel yet. So this is instead of doing the time-dependent CPV search, we also have the time-integrated CPV search that we can measure the decay with difference between the 0 flavors. That actually we can define the asymmetry as this equation, and this quantity can be large up to around 1%. And then we also did this analysis on the run-to dataset of the pion tag sample, that we can extract the nice sample of the D0 to K-shot. And after that, we have measured this asymmetry to be this number. The large uncertainty is related to the uncertainty from the control sample, in which we use the control sample to be the D0 to KK. Well, this number is still consistent with no CPV hypothesis at the 2.4 sigma, and this can provide with the most precise measurement up to date, comparing to the previous result. So the last one that I'm going to talk about is the lifetime of the omega C baryon, which is in the over the spectroscope, in the over spectroscopy. For the motivation, because it's in 2018 there was a charm hadron hierarchy, because it's on this inconsistency measurement of the lifetime of the heavy charm baryon. So on the PDG 2018 is a lifetime of the omega C is was measured to be the shortest one among those heavy charm baryon. But in 2018, we actually measured the longer lifetime of the omega C in the semi-leptonic sample, and it's we can have the lifetime of the omega C to be this one. And then it's so this provides as the motivation to conduct some cross-check result with an independent sample. So in this case, we analyze the data on the run-to formerly produced omega C and psi C that decay to p kk pi final state, and then we use the prompt D0 to kk pi pi decay as the control channel, and then just for the fit, we just estimate the lifetime with the least square fit to the decay time distribution in bin. And then in this case, we have extracted around 15,000 event of the omega C, and then around 50,000 event of the psi C. And then we have measured the lifetime of this to heavy charm baryon to be around this number. So as you can see here, the lifetime of the omega C is actually like longer than the lifetime of the psi C. And then it's like so this confirmed that the this actually confirmed the measurement of the this decay channel on the semi leptonic tag in the 2018. That we confirmed that the lifetime of the omega C is actually larger than the lambda C and also psi C, for example, or longer. Sorry. So in conclusion, LSCB has produced the largest data set of the charm hadron. This leads to the new interesting result and provide often the world-based measurement. So, and there are also like a more result coming soon, which are well a lot in the pipeline. However, it's like as you can see before, like the measurement are mostly limited by the statistic uncertainty. And this is expected to be improved in the run tree measurement, which is starting next year, hopefully, with the expected luminosity up to around 50 inverse femtobarn by 2030. So in the meantime, we are also working on the preparing on the upgraded detector as well as the upgraded online trigger. Yep, that's it. Thank you. Any questions?
Thank you very much. Are there any questions? Okay, I don't see any hands raised. I would be curious if I may ask. So you looked at the time-dependent CP violation in D2 pi and D2 KK. You have a result for delta ACP in the ratio of those CP violating asymmetries. Is there a plan to measure CP violating asymmetries, time-independent CP violating asymmetries in pi and KK separately? Not in the ratio, in difference?
What do you mean? I'm sorry.
So you have in this box over here, you have A sub F D, right? So that CP violation asymmetry, at least the way it was presented at LHCb was as a difference between CP violation asymmetry in KK minus CP violation asymmetry in pi, but never separately.
Yeah, right.
I would be curious if the separate measurements of those asymmetries are forthcoming.
I think there should be some like measurement, but it's like the thing is I'm not aware of that, or maybe I forgot about it. It's like I can look it up.
Okay.
Yeah, it's like it could be interesting. Yeah.
Right. Thank you. Last call for questions. All right. Well, this concludes our morning session. Thank you, everyone. Let's thank all of the speakers. And I think we are coming back here at 10:25 after a tea break.
Yeah, well, thank you very much to all the speakers of this session, and special thanks to our chairman, Alexey Petrov, who just provide this very important work for the conference just in the middle of the night, and we are thankful to his efforts just to maintain, to help the conference. Thank you very much, and we hope that next time we will be facing each face-to-face in the Lomonosov conference, and of course there will be no sessions for anyone during the night. Okay, well, thank you once again, Alexey, for your very important help.
Glad to help.
Yeah. So we shall meet at 10:25. Yeah, according to the time, same time, yeah, like it is in the program. Well, see you. Bye bye.